All right, so we are in generalized linear models with examples in R, and we are still here in chapter 2. A lot of questions here, a lot of multi-part questions that take a while to put together. So it's a multi-parter, and so we'll go through them one at a time. But so here's the question. Okay, so so the idea is that there was a hypothesis, or is a hypothesis, that babies would take longer to learn how to crawl in colder months because the extra clothing restricts their movement. Okay, so what this data? So we're going to look at a data set called crawl, and what it's why don't we just pull up the data set actually? So I'm just going to comment this out here so it doesn't screw up our screen. Okay, so let me. All right, so so I'm going to load this data from the. So first I need to install the GLM's data package, load it, get the data crawl, and then I'm just calling D here. Okay, so here's our data set, and what we have is the month that that babies were born. And then each month might have some number of babies that were born then, right? So here's sample size. So there was 32 babies born in January. There was 27 born in May, etc. Okay? And so the age is when they first started crawling, and it's the average of the 32 or the 36 or however many. There's also a standard deviation. I think it's in weeks here. There's also a standard deviation of when they started to crawl. Okay? And now temperature is the temperature, the average temperature of the month 6 months after they were born. Okay, so in other words, so temperature 6 months after. So 6 months after is when babies are about ready to crawl. So in other words, this is the temperature around the time when we expect them to start crawling. Okay. So so what we want to do then is we're trying to model age as a function of temperature, which again is the temperature about the time we think that they're ready to start crawling. Okay. So so I'm going to answer 1 and 2 together. So plot the data. Which assumptions, if any, appear to be violated? Geez. And then explain why a weighted regression model is appropriate for the data. Okay. So I'm going to actually plot a couple of things here. In fact, let me just get the plot going. All right. So let me show you what this plot is. Okay. So and each of these I have. Let's just look at this one right here. Don't worry about the other 8. So here we have temperature on the x-axis, and then age on the y-axis, right? We're plotting age as a function of temperature. Now the little black circles are the mean values that were estimated, right, from the data, right? The mean crawling age for babies born in months where 6 months later the temperature was whatever here. Okay, and then the vertical bars are I can't remember. I think that these are standard errors. I think that is standard error. No, it's standard deviation. Okay, so the bars are representing the standard deviation, the SD variable that is in the data set. Okay, now the little gray circles are me simulating data. Okay, so this is just me simulating data based on the mean and standard deviation of that month. Okay, now I've also added some jitter so they kind of go horizontal. So even though like all of these, for instance, would have been at temperature here, whatever that value was, I've kind of jittered them about so that it would so that you can see them more clearly, and also because the temperature certainly had some variation in it. So all that I'm doing with all of these plots, so the black dots and lines are identical, And then I'm just showing you what maybe different types of data could have looked like. Okay. I should also say that the number of simulated observations equals the sample size that was given in the data. Okay. So again, there's just several plots because I'm just showing what the data may have looked like over several simulations. Okay, that's all. All right. So again, you can look at the code. You can go to the Colab sheet and kind of see how I did all of that. But that's the basic idea. All right. So now we're meant to explain, what assumptions appear to be violated? And then the next question is, why is a weighted regression model appropriate for this data? Okay, so these two kind of answer one another. You know, we would use a weighted regression if, for instance, the variance, or in this case, the standard deviation across trials was not consistent, right? Because one of the assumptions of linear regression is that variance stays constant across all values of the explanatory variable, okay? Well, I guess that technically we know that that's not true if we look here, right? We have different values for the standard deviation, and so if we square those, it's the variance, and obviously different standard deviations are going to give different variances. But I mean, you know, I don't know, but these don't look drastically different, right? They don't look drastically different to me. Okay, so so I think that's the assumption that we're guessing should be violated. If you have a better answer, please comment for me. And so if that is the case, that it has inconsistent variance, then that's why a weighted regression should be appropriate. Again, however, I do not know that these variances are so wild that doing weighted regression is going to cause much of a difference. Well, in fact, I know it won't, because that's what we're going to do here in a little bit. All right. Now questions 3 through 8. So you can read these for yourself when you want to, but they're all covered in the next bit here. They're all so closely related. I didn't want to pull them out because I felt like it would kind of ruin the flow of everything. Okay, but what we're going to do is we're actually going to fit a weighted regression on the data and then interpret the coefficients. And so that's what I'm doing, but I'm actually going to do an unweighted version, right? A weighted version where I'm weighting on standard deviation, and then another weighted regression where I am weighting based on sample size. Now, standard deviation and sample size should be roughly related, right? Because the greater the sample size, the less the standard deviation, and so on and so forth. But anyway, so that's what we're going to do, and we're going to test the hypothesis that was proposed by the researchers, namely that colder months tend to lead to delayed crawling age. Okay, so let's do that here. Okay, so I have my 3 models. Okay, unweighted, weighted with standard deviation, weighted with sample size, and notice that the values really are incredibly close to one another, just as we probably would have anticipated based on the arguments I was making earlier, that the standard deviations don't look that crazy. You know, by eyeballing it, it doesn't look like the variance is really that different between observations. Okay, so anyway, we are also asked to find the 90. Well, they want the 90% confidence interval for the slope of the line. In other words, what is the 90% confidence interval for this term right here? And so we can do that with the conf_int argument here. Okay, and so down here the formatting is a little bit wonky, but it looks like this. Okay, so so the 95% confidence interval is from negative 0.13 all the way up to negative 0.02. Okay, and they're all very, very similar. All right. So when we want to interpret the coefficient here, well, then what we would say is that, okay, well, it certainly does seem that temperature does significantly associate with a decline in age of crawling. In other words, the hypothesis seems to be supported, because that would mean that colder temperatures have an increased age at which crawling occurs. Okay, so that is signified by these p-values. Okay. Now it's also signified by the fact that the 95% confidence intervals are completely below zero, right? They're all negative, 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 right? So a 5% confidence interval, if something is significant, then that suggests that a p-value that we deem to be significant at 95%, at 0.5%, means that the 95% confidence intervals, are going to be completely on one side of zero or the other. Okay. Now, notice that the question asked for 90% confidence intervals, and I gave 95, and I gave 95 in order to go along with the idea of calling it significant and p equals 0.5. So, okay. So, all right. So now we're going to plot the difference, or I'm sorry, we're going to plot all of these, okay, and also put a 95% confidence interval on the fitted values here. Okay, so so that's what all of this is doing. Okay, so I want to generate new data for temperature, so it's just going to be a sequence that goes the extent of the data, maybe even a little bit beyond it, and then I'm going to make predictions for each model here. Okay, so I'm going to make confidence intervals for the response at a level of 95%. All of this is wrapped in a for loop so that we could make many. Okay, so just like up here, I made 9 plots so we could just see how the simulated data could look. And here I'm just going to run it once, but if you wanted to, you could adjust these values so you could make it 3 by 3 and then go 1 to 9 or whatever. But let's just look at this. Yeah, let me open this up. All right. So so again, here we have everything. So we have temperature, age, and then we have the 3 regression lines here, and they're so close that they are just completely overplotted. The unweighted model is red, the weighted on standard deviation is green, and then there's actually, if you get real close, let's see if you can see it, there's little dotted blue lines, and that's the third weighted, okay? Or I'm sorry, that's the second weighted, where it's weighted on sample size. And then this band right here is the confidence interval for the mean. And notice that they are just completely overplotted to where they make gray. If you go to the margins, you can see how one confidence interval is poking out of that envelope there. But anyway, okay. Let me see. Is that it for this one? Yeah, I think that is it. Okay. So so we'll call that good, and we'll see you in the next one.